Assalamualaikum and selamat sejahtera. This video presentation is for our group project for subject Turbomachinery under Encik Suzairin bin Masri. So our group members is Khairul Azim bin Khairul Anwar, Muhammad Aminuddin bin Muhammad Nazri, myself Mukiz bin Mano, and lastly Putri Farah Ain binti Afandi. For introduction, radial flow turbines are utilized across industries to convert fluid energy into mechanical energy efficiently. Unlike axial flow turbines, they have a radial configuration, allowing fluids to flow outward from the turbine center. This design optimizes energy transfer, making them versatile in power generation, aerospace, and hydraulic machinery applications. Radial flow turbines are employed in steam and gas power plants, aircraft engines, and hydraulic machinery, with ongoing advancements aiming to enhance their efficiency and expand their usage. Ultimately, these turbines are crucial in achieving sustainable and efficient energy systems. For our task is, we have to design a turbine capable of extracting energy from the water flow in a river. The design must follow the specific requirements that are already stated in the instruction. So on the table here, we have the pump limitation, we have minimum and maximum value. Moving to design specification, we have two types of design. Pump specification for design 1 have value for each parameter near to minimum value, which is flow rate 0.04 meters cubic per second, inlet absolute flow angle 10 degree, inlet blade angle 120 degree, outlet blade angle 50 degree, inlet blade width 5 mm, outlet blade width 10 mm, inlet blade radius 300 mm, and outlet blade radius 100 mm. For pump specification design 2, we have value for each parameter near to maximum value, which is flow rate 0.08 meter cubic per second, inlet absolute flow angle 10 degree, inlet blade angle 150 degree, outlet blade angle 80 degree, inlet blade width 30 mm, outlet blade width 35 mm, inlet blade radius 500 mm, and outlet blade radius 200 mm.
Assalamualaikum warahmatullahi wabarakatuh. My name is Putri Farah Ain binti Effendi, metric number AD190078. I will continue our presentation with Design Analysis 1. So for the design specification 1, this is all of the value for the parameter. So the first thing that we need to do is to draw the velocity triangle for the design 1. As you can see at the figure, there is two velocity triangle at the inlet and at the outlet. For the inlet, all the parameter will be indicated as a 1, while 2 for the outlet. Since at the end of the result, we need to find the value of power and torque of the turbine, so we need to find the value of tangential velocity, V theta at the inlet and the outlet. So to find the V theta, we need to find the VR, which is radial velocity at the inlet and at the outlet first. To find the VR1 and VR2, so we can use the formula of flow rate, which is Q is equal to VRA. So VR1 is equal to 4.244 meter per second and VR2 is equal to 6.366 meter per second. Next, the value of V theta 1 and V1 can obtain by referring to the velocity triangle at the inlet. So V theta 1 is equal to 24.096 meter per second and V1 is equal to 24.440 meter per second. So the value of U1, blade speed at the inlet, can obtain by using the sine rule, which is U1 divided by sine 180 minus 10 minus 120 degree is equal to V1 divided by sine 120 degree. So we got blade speed at the inlet is 21.618 meter per second. The rotational speed of the turbine can obtain by using the formula of U is equal to R omega. So we got the rotational speed omega is equal to 72.06 radian per second. Next, the value of U2 blade speed at the outlet can obtain by using the formula of U2 is equal to R omega. So U2 is equal to 7.206 meter per second. To find the value of X2 and V theta 2, we refer to the velocity triangle at the outlet. So we got X2 is equal to 5.342 meter per second and U2 is equal to X2 plus V theta 2. So we arrange the formula. We can get the value of V theta 2 is equal to 1.864 meter per second. Since we have the value of V theta 1 and V theta 2, so we can find the torque and power of the turbine by using the formula. So for the torque, we got 281.372 Newton meter, while for the power is 20275.67 watt. The power value of 20275.67 watt indicates that the rate at which the radial flow turbine is transferring energy from the flowing water to its mechanical output. Specifically, it means that the turbine can convert 20275.67 joules of energy per second from the water flow into a mechanical work. So thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Aminuddin bin Muhammad Nazri. My metric number is AD190030. I would like to present on part design analysis 2. Based on the design specification 2, the value of the parameter is as follows. Flow rate Q is equal to 0.08 m meter cubic. Alpha 1 is 10 degree, beta 1 is 150 degree, beta 2 is 80 degree. B1, which is the thickness of the blade, is 30 millimeter, and B2 is 35 millimeter. For the radius of the inlet is 500 millimeter, and the radius for the outlet is 200 millimeter. Next, this is the velocity triangle for design 2. At the above, U1, V1, and W1 is at the inlet of the turbine, and for the outlet of turbine is U2, V2, and W2 at the outlet of turbine. Okay, now I would like to present on the velocity triangle design at the inlet and the outlet. Okay, for the inlet, we can get the absolute flow angle, which is alpha 1 equal to 10 degree, while for the blade angle at the B1, beta 1 equal to 150 degree. Next, for the outlet part, we can see the blade angle beta 2 equal to 80 degree. So, based on this illustration, we can get velocity ratio for the both of the blade angle, for the both of the inlet and outlet, which is VR1 or VR2 equal to V theta 1 or V theta 2 times tan alpha 1. Next, for the part of calculation, the formula of the flow rate is Q equal to VR times A. A is area. Okay. Area for the both of the inlet and outlet design is 2 pi R B. Okay. The value of the radial velocity VR1 and VR2 can obtain by using the formula of flow rate Q. Okay. As we see, VR1 equal to 0.849 meter per second. Then for the VR2 equal to 1.819 meter per second. Okay, we need to find the value U1, V1, and W1. Okay, by using the velocity triangle design to add inlet, we need to find V theta 1. V theta 1 equal to 4.815 meter per second. The value of the blade speed at the inlet U1 can be obtained by using the sine rule. After we do that calculation, we can get U1 equal to 9.629 meter per second. Okay. Based on that, U1 equal to R1 omega. We want to find omega, we just insert the value of the R1 and U1. Okay, the omega of the at the inlet is 19.258 radian per second. Okay, next for the velocity triangle design at the outlet, we want to find the U2, V2, and W2. Okay, for all, we can find the U2 through U2 equal to R2 omega. So we insert the value of the obtained, we can get U2 equal to 3.8516 meter per second. Then we want to find X square. X square equal to 0.321 meter per second. So when we get we want to get V theta 2 equal to negative 3.5306 meter per second. Last but not least, we want to find the power of the turbine. The formula of the power of the turbine is W equal to T omega. T is equal to torque as above calculation, and value we get for for the torque of the turbine, we get T equal to 249.09 Newton meter. So as we get torque of the turbine, we can calculate the power of the turbine. The power of the turbine is W equal to T omega. W equal to 249.09 times 19.258. So the power value we get is 4,796.98. Okay, the power value of the indicate rate at which the radial flow turbine is 4,796.98. So it shows that the turbine can convert 4,796.98 joule of energy per second from water flow into mechanical.
Alright, Assalamualaikum. Hi, my name is Karazim Anwar. So I'll be talking about the discussion. So to refresh back what we intended to the proposed design is to create a pump design that uses the kinetic energy of the water to rotate a shaft, and then the volume flow rate of the system ranges from 0.03 to 0.09 meter cube per second, which means the pump must be able to handle a wide range of water flow rates. So we have proposed to design analysis of the turbine, whereas the first design analysis of the turbine was conducted at the volume flow rate that was close to minimum requirement. This is to see how it would perform at lower flow rate. However, the second design analysis of the turbine was conducted at the volume flow rate that was close to the maximum requirement. This is to see how it would perform at higher flow rate. Okay, so the goal of the design is to ensure the pump can extract as much as energy as possible from a wide range of water flow rates. So the first proposed design for the water pump flow water from the river have higher power turbine, while the second had a lower power turbine. However, the second design will be better at extracting more energy. This is because power of the turbine is not only the factor that determines how much energy can be extracted from the river. Therefore, the second design has higher energy extraction capability, even though it has low power rating. This is because second design has higher volume flow rate, which compensate the lower power rating.
For the conclusion, the second design of the water pump, despite having a lower power output, is more effective in extracting energy from the river compared to the first design. This is because the second design compensates for its lower power output by having a larger volume flow rate. The volume flow rate is a crucial factor to consider when calculating the pump's capacity for energy extraction. By considering both the power of the turbine and the volume flow rate, developers can ensure the most efficient extraction of energy from various water flow rates. That is all for our group project. Thank you.